Hi, Dr. Godis.
Hey Tyler, welcome to the post-class video on the Nernst equation.
Right.
And remember, the Nernst equation is an equation that describes the relationship between voltage and concentration.
Okay.
Right? So in those tables, you look up standard potentials. Those are at 1 molar concentration. The Nernst equation allows you to correct for the fact that a lot of times you're dealing with concentrations that aren't 1 molar. Right, so in class we went through, used it in a fairly straightforward way. We gave you concentrations and you plugged them into that equation and calculated E. But this problem that we're going to walk through is a little bit different. It uses the Nernst equation kind of in a backwards fashion. And so it's always a good idea to see how you can use equations in different ways.
Okay.
So electrochemical cell based on the copper 2+, and silver plus couples at standard conditions has a potential of 0.4577 volts. Right? So that's what you get if you look at the tables, do cathode minus anode, da-da-da. So that's where we're starting. When enough sodium chloride is added to both cells, so you add sodium chloride to both sides to give a 1 molar solution, a white precipitate forms in the silver half cell, and the voltage changes to 0.170 volts. What's happening and what are the concentrations of copper 2+ and silver plus in the resulting cell? Assume no volume change when the sodium chloride is added, right? Added as solid.
Right.
Okay, wow. So we're adding a little bit of chemistry in here.
Which is the point of chemistry.
Exactly. And we're asking, what is the final concentration? We're not giving you the concentration as we calculate voltage. It's, here's the voltage, calculate the concentration.
Which is a little harder.
A little bit harder. But really the hard part is figuring out, well, what the heck is chemically going on here?
Right, so let's start with that.
Let's start with that.
We know that it has something to do with copper and silver.
Okay. And so to start off with, I just looked up these couples in the standard potential table and found that the copper reduction has a potential of 0.3419, the silver 0.7996. We don't really need those to do the problem, but why might I want to have found these out, figured out?
Well, because they can't both be getting reduced.
Right. So one of them is going to be flipped. One of them is going to be the cathode and one the anode, and so I wanted to figure out.
Right, and this will tell us which one.
Okay, great. This is the more positive potential, so that's going to be the reduction at the cathode. This is going to be the oxidation at the anode. And so now I can write my balanced equation. Okay, so I combine those two, and we need 2 silvers because there's only 1 electron there, there's 2 electrons there, the number of electrons have to transfer. And this also tells me, oh, I may need it, I don't know, n equals 2.
Right.
And this also gives me the coefficients in the balanced equation, so when I have Q, when I write the Q expression, I'll know what exponents.
Exactly.
Right? So you always got to write the balanced equation out. Maybe I should write out the Nernst equation.
That might be a good idea.
Okay. So I'm going to, this is my voltage for the cell, right?
Right.
That's what I'm given. So that's my E, 0.170 volts. This is my E0, right? That's the standard potential. So this is an equation I'm going to use. Know that, know that, know that. T, we'll assume it's standard temperature because I didn't say anything about it. N, we know that. N is 2. F is a constant. And so our unknowns are over here. Oh. And it's a square. Didn't I just make a point about having the balanced equation to know the coefficients?
Well, if not, I wouldn't have been able to catch that. Good thing we had the balanced equation.
Okay. So let's look at what happened. I added sodium chloride, and it says a white precipitate forms in the silver half cell. Huh. So what happened in the copper half cell? Nothing. It doesn't say anything happens.
Oh, okay.
I add the sodium chloride, nothing happens. And so what that means is that the copper concentration, copper, it's just sitting there still. Right?
Sure.
So this is still 1 molar. The precipitate formed in the silver side. So in the silver side, all I have is silver plus and Ag solid. That's already a solid. And so what must have happened is that the silver reacted with the sodium chloride,
Sure.
or the precipitate. What do you think that precipitate might have been?
Silver chloride.
Silver chloride, right? The silver, the cation, reacts with the chloride anion and forms a precipitate. You might remember from the first semester that the precipitation rules say that chlorides are soluble except when it's with silver or lead or mercury
Right.
1. Right?
There you go.
Okay, so it precipitated out and that changed the concentration.
Mm-hmm.
Well, now I have one equation. I know everything in there except for the silver. Right? So I can start to plug that in. And I'm going to rewrite this and put in all the values for the constants. You might want to check at home, try this, make sure that you can get it right. Okay, so that's it written out with all the values inserted. Remember to have this in kilojoules per mole, to match this kilojoules per volt mole, 298K. And then it's just algebra, right? So I'm going to consolidate, take this over to that side. Divide by the top, multiply by the bottom, i.e. kind of multiply both sides by the reciprocal. Oh my. And then I'm going to get this and that. I guess I'll write down one intermediate step. I kind of did all that algebra to isolate the natural log thing. And I got 22.4 equals natural log of 1 over Ag plus squared. Is that right? And then you just E to both sides, you isolate the silver, and you end up with getting silver plus equals 1.38 times 10 to the minus 5 molar. Voila.
And that answers our question.
And that answers our question, right? We know the copper, that was easy. Didn't change, it's still 1 molar.
Right.
The silver plus, we calculated the concentration there, right? Does it make sense? The voltage went down, it decreased. Does that make sense based on this reaction? We decreased the amount of the silver, one of the reactants. Is that going to favor the forward reaction or the backward reaction?
It's going to favor the backwards reaction.
Yeah, going to favor the backward reaction, or the forward reaction will be less favored.
Right.
So that kind of makes sense. And what we've actually measured here, we've actually measured the solubility of silver chloride. In the first semester we say that it's insoluble, it forms a precipitate. Well, it does, it forms a precipitate, but there's still a little bit of silver left in the solution. Right? Limited solubility. And guess what? The next section of the class, we're going to be learning about solubility products, how to use this as an equilibrium in an equilibrium calculation. So
Well
it kind
done.
of ties in there.
All right.
Yeah. Okay, so that's just using the Nernst equation in a little different way. Remember to write out your balanced equations and half reactions before you start, because that will allow you to kind of figure out what pieces are there, what pieces are missing.
Mm-hmm.
See you in class.